Okay, let's move on together. Let's move on. If you're still watching on YouTube or Facebook, it's one of the last chances to switch to OpenSlava.sk, where you get your registration, and we will put you up to virtual show floor where you can experience this conference in a much greater way with virtual avatars, with photo booth, AI bar, with the ability to chat with other visitors and meet new people, and also get into our competition for Nintendo Switch. And done for today. We're moving on to the next show. We're going to talk about scalability, but first of all, we need to switch to another system. Let's do that now.
Yep. All right. So, hello all. Happy to have you here attending this talk and hoping that you have had an interesting and engaging conference so far. My name is Vladyshevskyi. For short is Slava, it's my short name, and I will present this session today. Believe it or not, my name is Slava, exactly as a conference name. So it's been very hard to resist for me personally to not to join this cool event. So as a matter of further introduction, a couple of questions. Why should you listen to me at all? So first off, throughout my 20 years career, I've changed multiple roles in different industries and companies of very different sizes, having roles as a developer, sysadmin, project admin, project manager, architect, test manager, eventually consultant, which gives me a quite unique chance to look at IT systems and projects from very different vantage points and perspectives over quite extended period of time. I was also privileged to participate in developing some of the largest platforms and projects out there, seeing their inception, development, release, first baby steps, bumpy initial operation stage, maturity, and eventually reaching the steady state. At some point, I was a part of so-called SWAT team in one of the large companies I've been working for. And this team has been actually parachuted to most challenging projects, both to bring a fresh perspective and to unblock situations. Quite often, it's been related to managing through the largest outages and their fallouts, including root cause analysis, or as it's called, RCA, and improvement or mitigation plans. So yes, there are a number of battle stories I can share with you today, and even more if you will reach out to me afterwards, because obviously I cannot fit just everything I would want to tell today. Of course, all situations are very different, but surprisingly, root causes for most of them are very similar. And over time, they started to produce some recurrent patterns, which leads me to a second point here. So what is the real objective of this talk? It is very tempting to turn this talk into another system design conversation and choose and concentrate on a particular subject of interest and get all the possible depth. Looking to the time we have, though, I probably will stay on the surface and shape this talk as a set of battle stories, anecdotes, and lessons learned the hard way, along with some practical advices that you can take and start using pretty much today. So to put it simple, it's a kind of practical advice I could have given to younger myself in retrospective. Obviously, every advice has its own remit and context, and some do's may become don'ts in other situations. So I have attempted to select those examples and cases and lessons which are holding true for majority of times, and may help you to first critically assess your existing systems, prevent you from making some rapid rash decisions that may potentially backfire later on, or at least evaluate your projects from a completely new perspective you never thought about earlier. So my first advice is please, please, please document your decisions. Capture notes about the changes you make and decisions you make. And it doesn't really matter whether it's a group or your own decision. You can keep those notes and comments in the code or as a separate document with decision records under your code base. You can capture timestamp nodes without any particular structure, or you can follow the structure laid out by ThoughtWorks in their architecture decision records methodology. You can have a separate page in your wiki or Confluence. Main thing, just do it. The fact that you document decisions is much more important than the format you use. Au contraire, if you don't, prepare for all kinds of bad surprises, ranging from split-brain architectures to broken communication protocols, or even to some nasty outages during the operational phase. So the first thing which comes to my mind is a real-life story. Earlier in my career, one of our lead network administrators decided to configure OSPF on edge routers instead of BGP right before going on vacation. He slightly overestimated his knowledge and made a couple of mistakes. Suffice to say, he has kept all details about this change in his head on there. Although it wasn't a national ISP provider, memories about this situation, sleepless nights, and thousands yelling customers are still quite fresh. I believe that everyone here can relate this example to some story in your own career and practice. Still, surprisingly often, we decide or change system first, knowing that it has to be documented at some point and rarely coming back to actually do it. If we personally can recall that we changed or plan to document, there is simply no way for others to figure out or guess what we plan to do. So there are many more examples of this anti-pattern with one particular corollary. Don't overly trust your own memory. In teamwork, there's simply no way around clearly documented decisions and change records. Another one, don't trust your inputs, even those which you consider to be trusted ones. Now, there is no excuse, really, if you don't validate user inputs. This advice goes a little bit further, and I'm not talking about your direct user inputs. I'm rather talking about your backends, your trusted sources. So the point here, don't rely on those data feeds and data procedures and data producers. So if you think a database query will never have more than a handful of records, think again. It could change without you even noticing because of some other part of the system. So the only sensible numbers you can think of, it's 0, it's 1, and lots of them. So unless your query selects exactly one row, it has the potential to return way too many. Another real-life anecdote, application servers in the cluster started failing one after another with a JVM out-of-memory exception. And after a start, they were not even able to finish their startup, terminating with the same exception. So the root cause that was found much later was an assumption that the database table with cluster members information will contain just a handful of records. Hey, how big can your cluster be? Due to some other false assumption, this table actually grown and contained millions of records. So each application server loaded the table, took a record, instantiated the object, consumed memory, repeated with the next record. Well, you know the rest of the story. So the practical advice here, you can guess, unless your query returns exactly 0 or 1 record, limit the number of records. More generally speaking, use pagination or a sliding window over a larger record set. Another one, beware the code you can't see. You can't really trust the code you cannot see, as simple as that. And I'm not talking here about malicious intent, ransomware, or some built-in exploits, though such topics should be on your mind too. In this case, I'm more concerned about the quality of code, readiness for production use. So be warned, all types of issues can lurk in the shadows of a third-party code. Even if you naively hope that your vendor did some tests and proven this code functionality, you still need to perform your own bit of integration testing, load testing, etc. So You need to understand additionally how this code will behave in some edge and border cases and in various value scenarios. I do prefer open source libraries and code to closed source for this very reason. I have enough battle stories to share about bad outages caused by either JDBC drivers throwing an exception in the place nobody would actually expect, or the driver behaving not exactly as described by the vendor. Those were really huge disasters that actually made it to the headlines. So doesn't matter whether you're working for a large bank or airline company or even a little startup, the rule is the same. If possible at all, try to avoid the code you can't see, understand, and test. The next one, don't blindly trust aggregations. Well, you may ask, why? Well, they're hiding data. My favorite metaphor, two men ate a chicken. One ate the whole piece, another one ate nothing. In average, they had a nice meal. You got the point. So in IT, you may think of a system which is getting very short load spikes or bursts, so high load that it has to drop some packets. Those brief bursts are followed by a pause with no load at all. So the CPU load chart may give you a peaceful picture of about 50% load. No reasons for concern, right? In fact, this is exactly what happened in one project where applications and their throughput started to deteriorate without any visible reason. The only suspected place were virtualized network appliances, but they didn't really give any reasons for concerns. So their logs were clean and CPU were not overloaded. It took a while actually to understand what's going on after several days of troubleshooting and pretty much everything else being excluded. So the reality is, one way or another, we do need to deal with aggregations, such as averages over time, since precise point-in-time measurements are often impractical or even hard to do. Knowing this, at least, try to shorten time slice wherever practical, where you make this measurement to capture local deviations, exactly those peaks and lows, or at least underpin those aggregations with percentiles to understand what part of measured samples are above or below a certain threshold. By doing so, the data is not going to be more precise anyway, rather statistically substantiated. So you won't end up eating no chicken at all. Another one, as they say, always blame a network. So TCP was not designed for firewalls. So eventually the TCP protocol is some 40 years old, and it keeps up surprisingly well with modern network requirements. It works fine for the most part, but there are some edge cases where only packet capture would help revealing unexpected behaviors. Let's imagine your usual TCP three-way handshake, SYN, ARC happened between client and server, and data started flowing back and forth. Assuming no physical or logical interruption, this session can last indefinitely. It's not limited by the protocol anyway. Now, let's place the firewall in between. When a new TCP session is established, the firewall gets another record in its session tracking table, and all subsequent packets flowing between actors, client and server, are part of some session. So what's the problem, you may ask? Well, so far there is no problem yet. We shall remember, though, that firewalls cannot remember every single TCP session forever. And after a certain period of time, where no packets were coming either way, within established sessions, those sessions will be considered stale and removed from the table. Quite normal behavior. With an exception that TCP client and server know nothing about this change and continue thinking that connectivity is established and sending their data, which is going to be dropped since the firewall does not remember the session anymore. Depending on the TCP stack implementation and configured parameters, it may take quite a bit of time for the client and the server to figure out what's going on and to reconnect. If you imagine that it's your database connection pool threads are hammering on the firewall, while your application servers and your customers are waiting and waiting and waiting, well, the practical advice, the most obvious and straightforward, send keep-alive packets to keep your TCP sessions up. Yet better, implement timeouts in your application logic and fail fast. So you won't be spending time waiting just to find out that connection is dead. Continuing on the threads topic, let's face it, your threads will be blocked. This will happen inevitably, sooner or later. It may happen in your own code or vendor-supplied code. Third-party libraries are notorious sources of blocking threads too. Yet another reason to be cautious when using foreign libraries or code. The lion's share of all issues I've seen in production systems were caused one way or another by log threads. What's even worse, usually it's a vicious cycle. So under heavy load, concurrency growth, and rather sooner than later, it manifests itself in log threads. Whether you decide to remove a hanging instance from the load balanced pool or restart it, one end of the load will be added to surviving instances, which in turn will increase the load on them, concurrency further on, and so on, so eventually leading to a cascading failure. Is there anything we can do about it? Practical advice here? Well, if it's possible at all, consider alternative approaches, as in use event-driven non-blocking code. It can handle substantial load too, saying that if your choice is predefined and there is no way around threads, defend with timeouts. You cannot possibly prove that your code has no deadlocks in it, but you can make sure that no deadlock will last forever. And yes, avoid using libraries that you cannot test and instrument to avoid block threads. Another one, possibly my favorite, don't be afraid to question status quo. Some design approaches and decisions are so well entrenched, established, and have a demonstrated track record over years or even decades, to an extent that they are considered to be best practices or even design blueprints. The obvious advice here could be, well, use proven patterns and building blocks. While it's definitely a good advice, sometimes it's better to question the status quo and to try other and possibly new ways of doing things. Another anecdote. During the cloud migration project, we moved a MySQL database, originally backed by a disk-based Sun storage array, to a set of cloud instances backed by a full SSD storage stack. The overall performance and TPS, or transactions per second, throughput has changed dramatically. In spite of all expectations, it has actually decreased several times. Long story short, the new storage stack required complete departure from old design principle and paradigms, where you would normally keep your dirty pages in memory for a while and then flush them in large batches, resulting in long sequential writes, perfectly suitable for traditional storage arrays and controllers. The new approach was to flush dirty pages from memory as soon as possible. The memory allocation, threads pools configuration, and just about everything has been changed so that your average DBA would tell you that this configuration makes no sense at all and most definitely won't even work. It has paid off, however, and showed that we are on the right track. After aforementioned changes, the throughput increased significantly, even compared to original performance figures. It's hard to beat the test result, I would say. When your TPS number grows 10 times, even most skeptical naysayers are softening their stance and ready to listen. Thinking of this particular case, the following famous quote comes to my mind. What got you here won't get you there. In this case, meaning that the best setup in one environment that you possibly have right now most likely won't be the most optimal in a different environment. And don't forget, at times people achieved breakthroughs and innovations just because they didn't trust or didn't know the fact that it can't be done that way. Another one, often overlooked, by the way, design and architectural decisions are also financial decisions. More often than not, architecture and procurement departments are chasing very different goals. The former strives to deliver the most robust and sound design, doesn't matter what the cost is, and the latter is figuring the most cost-optimal solution, or often the cheapest option, which may not necessarily fit the architecture bill. Both parties are optimizing using different criteria, and those criteria are often in a reverse correlation, or basically pointing to completely opposite directions. In other words, the name of the quest is often becoming looking for the cheapest of the best options or looking for the best of the cheapest. Doesn't matter what is the precise name of this exercise, there are a couple of principles helping to steer and resolve this conversation. The first one, it's actually much easier for the technologist to assess the overall cost than for the procurement department to assess the technical feasibility. Second, sometimes the most expensive and feature-rich solution is not the best fit for your architecture requirements. So meaning, don't always choose the most expensive option because of all bells and whistles. And the third one, don't forget the big picture and the total cost. Think of long-term or the whole timeline. Systems spend much more time in their life cycle in operation than in development stage. At least those that made it to production do. Avoiding one-time development cost by incurring a recurring operational cost makes simply no sense. So in other words, financial evaluation may and should be a valid aspect of architectural decision record and provide a sufficient rationale for the proposed best option. However, a little precaution here. If you do premature cost optimization, it may actually add more issues than it solves. So don't start optimizing prematurely on this dimension as well. The next one, provide end-to-end SLA, yet better decouple your SLAs. So the industry expectation from a managed service provider, or MSP for short, is to provide the end-to-end service level agreement, or SLA. The reality, though, is that your system is not hanging somewhere in space in ether, and it's dependent on dozens and dozens of other systems and services. In other words, as a service provider, you have to retain service even when your upstream dependencies go down. If you do fail whenever they do, then it's mathematical certainty that your availability will always be less than theirs. Or other way around, the services you depend on should be of equal or higher availability than yours, which may be in turn prohibitively expensive or even not possible. So this is kind of an equivalent of the second law of thermodynamics. Service levels only go down, never up. In simple words, the chain is as strong as its weakest link. Most service providers are real optimists. Saying this, having my tongue in a cheek. So they are even claiming 100% uptime SLA on certain services, thus violating this second law of thermodynamics, in hopes that financial penalties, usually a part of SLA, are not going to be higher than the revenue itself. It's quite a slippery slope. So the practical recommendation here would be to shift the end-to-end SLA discussion towards the availability of a specific business critical functions or features in the system. So features that do not depend on any external party or service can have your maximum SLA, hands down. So features that do require third-party services, however, can have only whatever service level agreement third-party offers, degraded by the probability of failure in your own system. So this way, you can actually help your customer to reach the best SLA at the most feasible cost. So as they say, the best bang for the buck. So naturally, it also helps to factor into the conversation the cost of attaining particular uptimes as a comparison. Sometimes people demand, we need 5 nines. Sometimes it's sufficient to show how much it would cost, and you can continue with some other topics. Now, one of the paradoxical learnings, or quite controversial, so the earliest decisions you make are the hardest one to reverse. So those very early decisions about system boundaries or decomposition into subsystems, they get reinforced into the team structure, in the funding allocation, in your program management structure, or even in delivery timelines. So your team assignment, normally it's a first draft of your architecture. And it's terrible irony that your very early decisions are all the least informed. So in simple words, the most critical decisions have to be made when you know the list.
Slava, excuse me, we have 2-3 minutes, so if you could wrap it up and then we'll go on. Okay?
Okay.
Thank you.
So another ironical point, reversing or changing those decisions, however, can be quite costly and really hard to do by itself. So there is no silver bullet, or there is no crystal ball I'm going to give you, but there are a couple of guiding principles that may help you avoiding those pitfalls and large overhauls. So first of all, do shorten your design iterations. Second, make early prototyping a good practice. Third one, don't try to solve everything at once. Define and deliver an MVP, or minimal viable product. Avoid component sprawl. You can always split later, and it's actually safer to split later. And don't concentrate too much on your team structure. So it has to evolve naturally. So now, will those suggestions make your early decisions any simpler? Probably not. Instead, they will help reducing the initial stakes and minimize losses if initial direction or decision will need to be readjusted. So that's it, and I'm happy to answer any questions you may possibly have.
Yes, and we're back. No, actually, we are a little bit over time, and we didn't receive any questions from the guests. But thank you for this. There was a lot of interesting information. The good thing is that it's all your work and then your things that you experience yourself, and that was the funny and interesting part of that. Thank you for joining us, Slava. It was very nice having you, and have a good evening.
It was a pleasure. Thank you all. Bye-bye.
Thank you. Bye-bye. And we'll now take about 20 seconds for a small technical break. We switch to another system. We'll see you soon.